All right, guys, welcome back to our discussion of BGP in our CCIE program. We're on our last two topics for BGP. Today we're going to talk about something relatively, or last three topics I should say, relatively straightforward. It's actually something that we kind of alluded to when we were looking at aggregation in general in our last lesson. But we're going to take a look at how we can utilize BGP aggregation for the purposes of traffic engineering. It's really kind of similar to what we would see in the concept of summarization and leak maps and whatnot that we see in IGP, where we're always going to prefer, essentially from a routing protocol perspective, the longest match route over a shorter match route. So if we've got an aggregate route, for example, that's a /5 or a /4, and we leak out some /8s or /12s or whatever, those /8s and /12 routes would ultimately be preferred over the /4 or /5 route. And that's just a general routing principle in most routing methodologies. So the application in this particular case and the way that we apply leaking routes in this particular case is going to be a little bit different than what we see with some of our IGP counterparts like EIGRP and OSPF. How we can do this is either with filtering, so we can say, okay, I'm going to filter out specific routes to a particular peer, or we can do this with what we call an unsuppressed map in BGP. So when we're generating the aggregate, either we use the summary only keyword or we use the suppressed map. Suppressed map typically when we're trying to filter out what routes are going to be leaked out. So if we look back at our topology and we go take a look at what we were doing previously, we had some prefixes that were active on router 7, and those prefixes still exist. If I come into router 7 here and I do a quick show IP interface brief, you'll see those loopback interfaces exist, and we're going to go ahead, show IP interface brief, sorry. We're going to go ahead and originate those loopbacks, so we already are originating those loopbacks into the BGP process. So if I do a show IP BGP, I can see that those loopbacks are being originated by router 7 into the routing process, 140, 141, 142, all the way up to 149. All right, now previously we were actually performing the aggregation of those prefixes on router 4, which was our route reflector in autonomous system number 100. And those routes were being learned from AS51. But if we take a look at router 7, based on our topology here, we have several different ways to reach AS51 from AS100. And so we may actually be able to influence path selection by sending an aggregate in from router 7, originating the aggregate on the same router that's originating these individual links, and then leaking out individual longer match prefixes on individual links within the topology. So that's one option that we have in this particular case. And that would allow us to enforce some sort of policy decision or influence potentially the potential direction that the route's going to take based on a particular destination. So in other words, AS100 in this case is trying to choose, do I want to use the egress path from router 3 to router 7, or do I want to use the egress path from router 5 to 7 in order to get to this particular destination? And that's ultimately what we're going to try and influence by doing this traffic engineering with route aggregation. So let's look at the CLI. We need to make some changes, obviously. To make things a little bit simpler, I'm going to go ahead and shut down the link between router 1 and router 8 so that we only have kind of really one direction to get to AS51. But I mean, by extension, this process is still going to be pretty much the same regardless of whether or not that link is active. But since we're only trying to demonstrate one concept here, I'm going to just kind of make it simple. So we'll do a show IP interface brief. And just can't type that today. Show IP interface brief. There we go. And we're going to shut down the link on gig 03. So interface GI03, and we'll shut that interface down. All right, so now we only really have one way to go from router 4. If I go investigate the BGP table, show IP BGP, We will see those prefixes in the BGP table for router 4, and we can see that we actually have multiple paths that we can take. We can go over to router 5 through the 57.7 link, or we can go over to router 3 through the 37.7 link. In this particular case, we're choosing the 37.7 link. All right, now we'll talk about why that is and take a look at that, but the information that we're getting from the router, based on the topology that we have multiple egress paths at this point out of the network based on the standard BGP selection process. Now it's interesting that there was one thing I wanted to change here. Looks like 37 is being originated into BGP because it is listed as an available path from router 4. So let me check something real quick. Show run pipe section BGP. I tried to take out as much as the original configurations that we had in here from some of our previous exercises, but I don't really want the external links to be part of the process, the BGP process, because we want to take a look at some options with regard to sending in routing information. So let's see. Doesn't look like we've got a neighbor statement. We don't have a network statement. Show run pipe section route map. Trying to see how the 37 network is being originated into BGP. It appears as though it's coming in as an internal route. Match interface loopback 0, permit 10. Redistribute connected route map loop. Show IP BGP. So it doesn't look like this router is originating that prefix. We're also seeing the 57 prefix come in as well. Somebody's originating this prefix. We shut down the link between router 8 and router 1. So I'm curious if it might be router 5. Show run pipe section BGP. It might not really pose much of a problem for us in our configuration. It certainly won't affect the overall understanding of what our objective is in this particular case. But I am trying to, so the 57 one is there. We want to remove that. And that's why the 37 one doesn't exist. All right. But I'm still curious why the show on pipe section route map. I'm still curious why the 37 link is showing up in router 4. Show IP BGP. Okay, that looks better. Well, it looks pretty much the same. Let me do a clear IP BGP star in. What I'm trying to do, I'll explain kind of what I'm trying to do a little bit later on, but the curiosity that I have here is that we are selecting this as a best route, and it says that we're going directly to router 3, which is fine. If I do a show IP BGP for 140.0.0.0/8, I can see that if this one shows as inaccessible, which is what I'm trying to create from router 3, somebody is originating the 37 subnet. It looks like it's got to be coming from router 3, but I'm not seeing that. In the BGP configuration. I'm wondering if it's router 7 that might be originating that prefix into BGP. Because I've got redistribute connected route map loop. We already confirmed the route map. I don't have any network statement for 37, so it must be router 7. That's originating that. It's the only other router attached to that segment. me a second now. 7777. Huh. Very, very curious. All right. Well, we'll leave that for now. It might not take too long. It probably won't affect our overall goal in this process anyway. So we'll go ahead and leave that for now. And if it becomes an issue a little bit later on, I'll try and correct the issue as part of our process as we move forward here. All right. All right. So anyway, remember what our overall objective is, right? Regardless of however the decision is being made right now. We're getting all those prefixes at router 4, which is our route reflector in the topology. And we're making a decision on how to reach those destinations based on information that we're learning from our peers. And we're seeing those individual prefixes as part of that process, okay? And we have multiple ways of reaching that particular destination. We should actually have 3 different ways of reaching that destination. We should see it from 57, we should see it from 75 and 37. We're not presently, but that's okay. We'll get that issue resolved when we configure or readjust our configuration with our neighbor relationships. So with regard to how we're reaching particular destinations right now, we could walk through the process. We're redistributing our loopbacks into BGP. We're not redistributing the directly connected links into BGP, so I'm not sure why the 37 network is showing up there. But again, it's not really going to affect our overall goal here, which is to understand how we're going to handle route manipulation or path selection manipulation based on leaking out or using an unsuppressed map with aggregate configurations. So the advertisements are being, we are definitely seeing the advertisements in the rest of the network. We're getting down to those routers. Everybody has kind of a different choice on how to get to those routers. Certainly router 2 is probably going to go over to router 4 to reach those destinations. Actually, it looks like it's going, well, router 3 is actually identified as the next hop. That's really, really annoying. Let me do something else here. Let me do a clear IP BGP on this guy as well. And also in, because the only reason that the 37 network should be originated into BGP is if I'm either redistributing it from an IGP and we have that network participating in the IGP protocol, or if I have a network statement or I'm doing a redistribute connected that includes that particular interface. If I do a show run section route map, we can see in this particular case that we're just simply matching the loopback interface, and only the loopback should be included in the redistribute connected process. So I'm very, very curious as to why that particular interface seems to be showing up as a valid next hop for these particular routes. Let me try this, clear IP BGP in. I did have some residual configurations in here from the previous exercises that we were doing, but what I would expect to see in this particular case is that, let me do this, do a show IP Ceph, see what we're matching against that, 172.16.37.7. We are matching it. So we are definitely learning about the 37 network somehow. Just very curious as to how we're learning that. Let me do a show IP route. Maybe we're learning it through an IGP process. That's exactly what's happening in this case. The 37 subnet is probably coming into us from, EIGRP. So let's fix that problem as well. Show run section router. So BGP is saying, hey, these prefixes are perfectly reachable because guess what? I'm learning about how to reach those destinations from, or that particular next hop address from the IGP routing process. And I'm trying to get rid of that for a specific reason in this case. I'll explain why in a little bit here, okay? So let's go ahead and remove that 172.16 network from the EIGRP process here. And actually, let's look at our topology. I don't want to remove it all because I still want to maintain my relationships here, but let's get rid of 37. We can't make it a passive interface because it'll still be part of the routing process, but we can add the 34 and the 13 subnets and then just remove the other statement there. So router EIGRP 100, network 172.16.34.0, 255, and network 13. Oops. And no network 172.16.0.0. All right. Now, the end result of this should be that R2 should no longer have. It should be learning about the prefixes through BGP, but it should not try to install that into the BGP forwarding information base. There we go. That should be. That's what I wanted to see. All right. Now, the reason why router 2 is not getting this information is because router 2 is a route reflector client from router 4. And if I do a show IP BGP on router 4, I should see those prefixes. This is exactly what I wanted to see. So I should see those prefixes, but we're not able to route to those particular destinations because those directly connected links to our eBGP peers are not part of the BGP process. There's a specific reason why I'm going through this process, and it does have to do with the topic that we're discussing, but it also doesn't have to do with the topic that we're discussing. It's just a general concept that you have to understand within BGP. So I'll get to that in a little bit here. So the routes are being processed by router 4, which means they're also being learned by router 5 and by router 3, and of course router 5 and router 3 know how to reach those destinations. The reason why I'm only seeing one link from router 5 is because router 5 is making a decision on which link to use. If I come into router 5, show IP BGP, I can see for those external prefixes that I actually have two choices. I can either go over to the 75 link or I can go over to the 57 link. I chose the 57 link, so ultimately that's what's going to end up being advertised to router 4 because router 5 is a route reflector client of router 4. So we don't see all three paths in this particular case, but we do see two options. Okay. Now there's a way that we can influence this path selection process. We can use all the other attributes that we talked about, weight and local preference and AS path and MED and whatnot, but we're going to look at it from a different perspective. So router 4 should be reflecting the routes over to router 1, router 2, and then possibly back to router 3 and 5, which 3 and 5 would simply ignore, but router 1 and router 2 are not hearing these prefixes because we don't have next hop processing set up correctly in this particular case. All right, somehow all these routes are getting to the other routers, but before we do anything else, especially based on aggregation, I need to fix the next hop processing so that we can actually see these multiple egress paths, and on top of that, those paths would be usable based on the fact that the loopbacks are part of our IGP routing domain. So I'm going to go into router 3, and this would be a typical configuration that you would do with BGP, section BGP. You wouldn't normally insert the directly connected or physical links to your eBGP peers into your IGP process. So what I'm going to do is I'm just going to go ahead and modify the attributes for my peers. So config T router BGP 100. And I am going to specify for my neighbor that any advertisement routes that I send to that neighbor, I'm going to advertise myself as the next hop. And we should see immediately on router 2, show IP BGP, that, well, let me clear IP BGP star out, resetting my routes out, and I should see from that change that this router now has access or reachability to those external prefixes. Because router 4 knows how to reach 3.3.3.3, we established the next hop for those routes is 3.3.3.3. So now these are reachable destinations. I'll do the same thing on router 5, show IP BGP summary, and I'll go into router BGP 100, neighbor, and 4.4.4.4, next hop, self. Okay, so now when I go look at router 2, I doubt that I would actually see any change here actually, well, especially since I didn't clear the session, clear IP BGP star out. I probably won't see any change in router 2 because again, router 2 is only going to make its decision on how to route to that destination based on how router 4 decided to make a decision on how to route. So, but if I do look at the BGP table for router 4, I can see that we have 2 choices here. We could potentially have 3 if we had a third router or a third path. In this case, we only have 2 because router 5 is eliminating one of those choices by making its own decision on how to reach a particular destination. Okay, so we don't necessarily have to worry about that too much. That's a backup path. Our influence is going to be between the primary path to router 5 and the primary path to router 3. Okay. All right, so we've modified the next hop value. We're now learning about routes from these eBGP peers. Router 7 is sending in these routes. Okay. So we have internal neighbor relationships. We're in AS100. We have internal neighbors specifically between router 3 and router 4, router 5 and router 4. So what we want to do is make sure that all of the normal BGP operations are taken care of before we start to modify some of the extended BGP operations or look at some of the options that we have with changing how BGP functions. All right, it's a very, very important concept. Make sure you understand how peerings work. Make sure you understand how the peerings are formed, how next hop attributes are being advertised, and so on. Because what might end up happening, and I think I ran into this last night as I was trying to kind of prepare for things, is you might be making some changes in traffic engineering, and the change that you make doesn't actually affect or have the desired effect that you would expect it to have based on that particular change. All right, maybe you want to route to one next hop in this direction, and you think that you set up the appropriate manipulation for that to happen, but then you end up routing in the other direction. So we did the same thing on router 5. Ultimately, BGP is always going to be configured as an application. We have to use our IGP process to choose the path towards the next hop. So we've cleared out the BGP routes. We still have our multiple egress paths. Now those multiple egress paths are usable, and we can go ahead and do a trace to our destination. So if I go, for example, to router 2, and I do a trace route to 140.0.0.1, I can see that I'm going to go to router 1, then to router 4, then to router 1, then to router 3. It's interesting that I'm going to router 1, then router 4. Interesting. Let me do a trace. Well, we're not sending in, we don't have full reachability because we're not sending in those internal leaks. Let me see source 2.2.2.2. That should result in us being able to reach the destination because router 7 should have a route for 2.2.2. Show IP BGP. It does not. Of course, the one router that I choose doesn't. So that's another thing that we'd have to fix. Let's make sure we're originating that prefix into BGP. So show run section BGP. And make sure we're originating that loop back into, yeah, that it doesn't look like we are. So configure terminal route map loop match interface loopback 0 and router BGP 100 redistribute connected based on route map loop. Show IP BGP. Now we should see the two network listed there, and we should also be able to do our trace route now. There we go. That's what I expected to see. So it looks like we're going over to router 4, which is expected. Yeah, same thing tomorrow, Gil. All right. We're going over to router 4. Then we're going over to router 1. Then we're going over to router 4. Then we're going over to router 3. But we're definitely going through router 4 and then to router 3 and over the 37.7 link to reach that destination, that 140 loopback on that router. It looks like we're actually kind of swapping between different paths. Going 1 to 3, 3 to 4, 1 to 3, and that's fine. That's not a problem because we're essentially, we can reach router 3 in multiple ways. Remember, to get to 3.3.3.3, I'm not using BGP, I'm using my underlying IGP, and that would be EIGRP, which if I did a show IP Ceph for 3.3.3.3, show IP Ceph for 3.3.3.3, you can see that we're using two different links to get to that destination. So it's again part of that recursion process with BGP. We're going to use the underlying IGP to make routing decisions. But in the event, we can still get there, right? And ultimately, we're still going to router 4 to get there. It's just a matter of how we get to router 4, all right? Which makes sense because router 4 is the route reflector. Now, let's say we somehow want to split the load of the traffic as it's leaving AS100 and going over to AS51. I could certainly do this by, if I go to the diagram, I can influence outbound policy by doing AS path prepending. I can do weight or local preference. I can do MED if I want to influence the traffic inbound. I can do AS path prepending inbound as well. And we talked about a bunch of different methods that we can use. By changing the local preference or weight inbound, that would essentially affect our outbound flows. So we could apply different weights or local preference to the prefixes that we're learning from router 7. Or we could set AS path prepending out or multi-exit discriminator out from router 7. And that's going to affect essentially how traffic comes back in. We also saw that the inbound policy can always override an outbound policy. That means if we're looking at the traffic from AS100's perspective, if we always want the packets to enter on router 5, just assume the bottom link, right, not the backup link, but we want the traffics to enter on router 5 as the primary, we want packets to enter router 3 as the backup, we could do prepending or we could do some sort of multi-exit discriminator manipulation, but there's nothing to say that on the other end of that peering relationship that they're not going to override this with weight or local preference. So one of the ways that to more accurately do traffic engineering for the return traffic is to selectively advertise longer match routing, right? And so aggregate these addresses and then selectively advertise longer matches. So we previously saw in our BGP tables that we have /8s. Those /8s exist pretty much everywhere in our topology now. If I go over back to router 2, I can see all these /8s in the topology. There's a couple missing there. Let's do a show run or show IP BGP pipe include 1.4. Well, let's do this. Include 0.0.0./8. And these are the prefixes that we have. So if I take those prefixes and I put them into Notepad, we can see as far as calculating an aggregate, we know that the 128 bit is set on each of those values in the first octet. In fact, the 128 bit is set, and then if I do 140 minus 128, that should be a 12, but it's been a long day, so we've got, in this case, the 8-bit set and the 4-bit set. All right, so 128 on the second one, second prefix, the 8, the 4, and the 1. So let me just do this in binary because it'll be easier to see. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And then 142 would be 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And then, so that's 140, 141, 142, 143. 144 would be, oops, and 145, and 146, and 147. No, that's got to be odd number. And 148. And finally 149. All right, so those are each of our octets, or each of our network subnets, our /8 prefixes. We're going to look for essentially our summary boundary, which is going to end up being at this point within the network, because those are the only bits that are common to each of those addresses. All right, so our prefix, our summary, is going to end up being 128.0.0.0 slash, in this case, 3, actually, not a /5. So we're going to advertise a /3 prefix. Now that's going to include a lot of other addresses, but that's the best summary we can come up with to match each of these prefixes that we're trying to summarize or aggregate together. All right, so we got a bunch of /8s. We're going to end up having them reduced down to a /3. Basically in the same principle as we're dealing with in IGP protocols. In BGP, we have multiple ways to apply this because in BGP, policy application is extremely flexible. But we're going to go into router 7. We're going to start originating this aggregation. So on router 4, we can go in and see that particular prefix. So let's go into router 7 and go into the BGP process, router BGP 51. And we're going to use the aggregate address command. And we're going to say 128.0.0.0 with a subnet mask of 224.0.0.0. And we're going to do a summary only in this particular case. We'll talk about all these other options a little bit later on. Some of them we've already actually seen in some of our previous exercises. But right now we're just going to generate this aggregate into BGP, which includes essentially all of those 140 subnets plus a lot more. All right, but it definitely includes those 140 subnets. If I go to do a show IP BGP, I should see that the subnets are listed, and because I did the summary only in this router, I should also see that the subnets are listed, but they're listed as suppressed. So we should see a lowercase s indicating that these prefixes are being suppressed, and only the aggregate is going to be sent to the peers. So IP BGP. And sure enough, we see in this particular case, there's the aggregate. It's going to be advertised, and each of the individual prefixes are suppressed, which is what the summary only represents. All right, so we could count this as a method for filtering out individual prefixes, and that counts. We could also do a suppress map, where we could say, okay, we're only going to suppress specific prefixes, and then allow all the other longest match prefixes to be advertised. So an unsuppressed map is kind of the opposite of that. We're going to suppress everything except for these prefixes. A suppressed map means we're not going to suppress anything except for these prefixes. So it really depends on, how many networks you're going to end up suppressing, as opposed to allow through. Will determine essentially how you decide to apply the policy in this particular case. All right. So let's say, for example, now I want to verify that router 4 has reachability to those prefixes. Certainly, if I do a show IP BGP, I can see that I'm only going to see the summary. But if I do a show IP Ceph to 140.0.0.1, I can see that it does match that particular route. And I can verify that in fact all those routes are going to match, but presently we're using the /3 prefix to see those particular routes. In this case, the only difference between the path selection process that we made before and the path selection process that we're making now is we're matching on a shorter match versus a longer match. All right, so it ends up essentially being the same thing. We haven't really changed anything. We just changed the size of the database and limiting the number of routes that are being advertised. Nothing really changed in the actual path selection algorithm because the paths didn't change and the attributes didn't change. Okay, If I did this for 149, I would see again, even if I did it for longest match, so I did 149. Let me see if this will work. 0.0.0/8. Yeah, prefix not found. So we'll just try it based on packet. Too many. There we go. So we can see that we're definitely able to reach these destinations. All right. Now, this is then where we get into kind of the more specific path selection process by leaking out specific routes. Since R7 has done the suppression, it's also the router that we should configure the unsuppression on. So specifically, we want to advertise those. Well, presently we're advertising the /3 in all directions. But let's say I want to pretty much influence how routes come in from router 5 and router 3. And presently we have those two paths. We have a third path, but we're going to assume that that path is really just there for redundancy from router 5's perspective. So let's say, for example, I want to advertise the 140 and the 142 prefix over, so that we come from router 3 in that particular case. And for the 141 and the 143 prefix, we're going to advertise that so that we come, well, let's do it the other way. We'll do the 140, since that's on top. 140 and 142 is going to come from router 5, or we're going to use router 5 for those paths, and then from router 3's perspective, 141 and 143 are going to be used. All right. We're still going to advertise the /3. We still want to advertise the /3 in both directions, and that's primarily for the purposes of redundancy. If a route fails, I want to be able to fail over to or fall back to that longest match route, or shortest match route, excuse me, and since the longest match route is no longer going to be available. So if one link goes down, we don't want to just filter out the routes or filter out the specifics, and because we're sending the aggregate in both directions, we'll still maintain reachability in that particular case. If we're trying to do longer matches, it's pretty simple. We just basically prefer one ingress path over the other, but we still do want to give them the option to fall back to the shorter match if it's necessary, if a link goes down or if those longest match routes are no longer being advertised. So that's why when you look at the internet table, you'll actually see that generally there's a lot of overlap between certain address space, and that's because someone is trying to basically divert or poke a hole in the aggregate to say, hey, I want to accept traffic for these destinations in here and then accept traffic for other destinations in a different direction. Okay. Now, specifically to do this, when we go into router 7 and we look at the aggregate statement, let's go to router 7. Let's take a look at the aggregate statement. Do show run section BGP. Show run type section BGP. Oh my goodness. I got up at 5:30 this morning to teach another class, so it's been a long day for me. But if we look at the aggregate command here, we can see that we're essentially suppressing all of the longest match routes because because we have the summary only option. But if I come in here and I go to router BGP 51, and we look at the options that we have with this aggregate address command, we have several different options that we can choose from. All right, and presently we're using the summary only option. If we take a look at the other options, we talked about summary only, right? That means that let's go ahead and filter out all of our specific routes. Suppress maps means that we're going to conditionally filter specific routes, if you will. The AS set, we talked about that in one of our previous exercises. That's where we're going to generate the autonomous system path back into the route. Same thing that we have with the confed AS set, but that would be for confederation peers. Advertise map conditionally says that based on the AS set, how are we going to advertise the prefix, and then the attribute map and the route map is just a way to set parameters of the aggregate itself. But we don't see here is how do we leak specific routes out to the peers? Well, there's a reason why we don't see that. That's because that is something that's applied on a per peer basis, not in the global routing process. All right. So when we issue global statements, the global aggregate that says suppress map or summary only, that's going to affect all of the advertisements for BGP. But if we want to selectively say what goes from 7 to 5, I want to leak individual routes, this would be applied under the neighbor statement for that particular peer. All right, so for this particular peer or neighbor, we could say that we want to unsuppress or selectively advertise previously suppressed routes to that particular neighbor. This is basically the equivalent of a leak map in some of our IGP applications, but we have a little bit more control in BGP because of the application nature of BGP. So our next step would be to figure out what are the actual conditions that we want to match. If we have 2 routes that we want to leak out to router 3, and we have 2 routes that we want to leak out to router 5, the first step would be to classify those particular prefixes. We could do this based on communities, which we'll talk about in our next lesson. Or we could do this really based on any attribute of those particular prefixes. It doesn't actually have to be a community. Anything that we can match against from a BGP perspective, we can apply to unsuppress those particular routes. It's basically anything inside the BGP update, and we can call that information from the unsuppressed map. So we have a lot of flexibility because essentially, I mean, for lack of a better term, the unsuppressed map is basically just a route map. All right, and we're pretty familiar with how route maps work at this point. All right, the unsuppressed map is essentially how we are applying the route map in this particular case. All right, so let's say we're going to create actual classification methods. So on router 7, we're going to basically do this with 2 different prefix lists. I mean, there's probably an easier way to do this, but since we only have 4 routes that we're concerned about, and before I do that, I always want to make sure, before I start to apply any kind of filtering to BGP, then I would be remiss if I didn't check to see if those prefixes existed in my database first. All right, that's the first step. So 128 is there, of course. That's what we're advertising. 140, 141, all the way up to 149 are suppressed, but they are in the database. So we know that we can kind of originate these prefixes to our peers. So let's go ahead and create our prefix list, IP prefix dash list, and we'll call this 2 underscore R3, and we're going to permit, in this case, 141.0.0.0/8, and we'll do the same thing for 143. We could match on different conditions if we have to. This is just one of those options, and it's a pretty simple option. So eventually, if we decide that we want to be more specific about how we're matching a particular prefix, then that means that we probably just need to create a route map to match those conditions, and then we can reference that route map in this case. And I mean, that's essentially what we're doing in this case. We're going to create a route map and match the prefix list, and then we're going to use that in the unsuppressed map. All right. So let's go ahead and create our ones to router 5 as well. And router 5 is going to be 140, and router 5 is going to be 142. All right. So that's first step, and you guys should be completely aware of how these prefix lists work at this point. We've talked about it many times. We've seen several examples on these prefixes, so prefix lists. So that's how we're going to classify it. And then all we have to do is create 2 separate route maps. We'll call one route map, route-map. Let's just do unsuppress to R3. And we are going to match the IP address prefix list to R3. Sorry, I had to sneeze there. All right. Let's go ahead and create another one to R5. And in this case, we're just going to match prefix list to R5. Okay. Now notice we're not really matching on any particular condition of the route. We're just simply matching the route itself. We could, if we wanted to, match on metric. We could match on local preference, weight, any kind of attribute that's sent along with the routing update from the peer. In this case, we're simply matching on the route. One key thing, though, to understand about the logic of this particular route map is that the permit means that you are going to leak the route, and a deny means you wouldn't leak the route. That's why we're not putting the kind of implied or explicit permit at the end, because then we would just simply leak out everything. All right, so a deny means that we're not going to leak the route, but we would still continue to advertise the aggregate because that was applied to the entire BGP process. Now, when we get these multiple attributes, you know, where we're matching, we've got BGP doing some sort of matching on its best path selection process, and then we're also leaking routes out and whatnot, we can run into some issues of order of operations. And we'll talk a little bit about that later on towards the end of our lesson here. I'll demonstrate one other concept for you real quick. All right. If we're trying to do route leaking, plus we're trying to do some sort of attribute manipulation, like within this particular route map, we need to understand that the order is going to be different depending on if we're manipulating those attributes inbound versus outbound. It's not necessarily something that you guys need to know for the test. It's not something that you're going to need to memorize, but and I'm probably not going to spend too much time on it for that reason, but in a production environment, you need to understand that if you're combining these different methodologies, you're going to get some unique behaviors with these match conditions and set conditions. So just make sure that you kind of test it out. If it doesn't work, you move the attribute to an alternate place, apply it to a different place within the application, and then you can see if that assists or that works a little bit better in your case. All right? All right, so we've got our prefix lists, we've got our route maps. Pretty much now, the only thing left would be to apply the unsuppressed map, which is essentially a route map, to the peer, right? So we're going to go into the BGP process. Let's do a show run pipe. Do a show run pipe section. What's going on there? Do show run pipe section BGP. And we're just going to apply these route maps to our peer. All right. I don't know why it's running so slow today. It's kind of annoying. All right, so we're going to router BGP 51. And we're going to go into neighbor 37. Now, in 37, we wanted to apply an unsuppressed map using route map. And in this, actually, we don't need to use the route map keyword. We just need to reference the route map. So we'll just go to R3. And then for the neighbor for 75 and 57, we'll do unsuppressed map, unsuppressed map. Come on. Oh, I got neighbor twice there. Unsuppressed map to R5. And the same thing for 75 to R5. And we do want to do a clear IP BGP star out because we are changing how we're advertising prefixes to the peer. So if I do a show IP BGP, I should see based on my configuration that specific prefixes are no longer being suppressed. Why did that not work? To show run section prefix route map BGP. Show run section prefix route map BGP. Let's see. we should not be suppressing. Well, I'm curious. Let's check a different output here, because we've definitely applied the unsuppressed map to the neighbor. The prefix list matches the prefix 141.0.0.0/8 and 143. Those are permits. The route map is a permit. I see what the problem is. I referenced the wrong name. I referenced the prefix list. I did not reference the route map. So let's fix that problem. Router BGP 51. And let's go into here and let's call that unsuppressed to router 3 and neighbor here, unsuppressed to router 5, and lastly this neighbor here. Because this configuration has a negative connotation, meaning that we're overriding the default behavior. Because I didn't match any conditions in a route map, because the route map didn't exist based on that name, only the prefix list exists based on that name, nothing was actually advertised out to the peer. Well, there's another way we could check this. We could do a show IP BGP neighbor, and we can type in 172.16. Let's do the 37 one for now, 37.3 advertised routes. And I can see what I'm sending to that peer. All right, so it actually shows me that they're still suppressed locally, but I'm overriding that behavior and I'm advertising 141 and 143 to that particular neighbor. So it's interesting if, and I thought this might be the case, if I do a show IP BGP, it still shows those prefixes as listed as suppressed, even though they're technically not suppressed. If I go into my neighbor for 57.5, I can see I'm advertising 140 and 142, and if I go to 75.5, I should see the same thing. 140 and 142 are being sent. So you can't always directly reference that code because that code isn't always, well, locally certainly it's showing that those prefixes are still being suppressed. Yes, sir.
I'm seeing an S on those as well. Does that mean that they're suppressed there too?
They're suppressed locally, but I'm actually identifying the prefixes that I'm advertising to the peer. So these prefixes should show up in the BGP table of these particular routers. If I go to router 5 and I do a show IP BGP, I do in fact see the 128, and I see 140, which is coming in over the 57 and the 75 link. I see 141, but that's coming from router 3, which is fine. That means that I'm essentially suggesting that I need to go to router 3 to reach that destination, and 142 is coming in over 57 and 75. So it's an interesting point that it does show that they're suppressed on router 7, which is technically true, but they're still being advertised. So and this is where the order of operations comes into play. If you were just to rely strictly on the local BGP table, you might think that those prefixes are being suppressed, but they're actually not being suppressed. We're actually advertising these routes. They're still in the local routing table, but they are getting advertised and being leaked out to those individual peers. So like I said, if we looked at the prefixes on router 5, go back to router 5 here. If I look at the prefixes on router 5, I can see that 140, and I even have a path that I can use to get to that destination. And 141 does have a path, but it's through router 3. 142 has a path. 143 has a path. But I'm not seeing the 146, 147, 148, 149. Those are still being suppressed, right? Interestingly enough, I am using router 5, the 57 link, to get to the aggregate as well. So even though we're learning about that aggregate through 3 different paths, we're learning about it through 57 and 75 and router 3. All right. So if I go to router 2 and I do my trace route to 141.0.0.1, oops, trace route to 141.0.0.1, I see that I'm going through router 4 and then through router 3. All right. If I go to 140, I should be going through router 5. So I'm going to router 4 and then I'm going to router 5 to reach that destination. I didn't do it sourced from the loopback, so I'm getting a timeout on the final one, but it's working, right? And it was a really basic configuration. We just went into router 7. We set up, the first step was show run pipe section prefix. First thing we need is to find a way to classify these particular routes. And we did that with a prefix list in this particular case. But again, it doesn't matter what the conditions are that you're matching, because ultimately you're going to match these conditions in a route map. And so I could leak out a prefix based on local preference. I could say, okay, well, if I'm receiving, not local preference, but a MED or AS path. If I'm receiving an AS path of XYZ, then I'm going to go ahead and leak this route out. If I'm receiving a MED value of this, I'm going to leak this route out, and so on. So we see that here we've got our prefix list to match those specific prefixes. And then if we do a show run pipe section route map, we can see in the route map that we actually have, we're matching those conditions, those prefix lists. And again, a permit in the route map means that we are going to leak the route, which is overriding the suppression that we have configured. All right. And there's our route map. Unsuppressed to router 3, match the prefix list, unsuppressed to router 5. And then finally, in our BGP configuration, we have a reference to the unsuppressed map, the route map through the unsuppressed map statement, saying let's go ahead and override the default behavior and let's let these routes leave the network. All right. But we'll still suppress the other prefixes and rely on the aggregate to reach those particular destinations. All right. The key difference here is that the suppression happens globally on the aggregate command, and then the unsuppression happens on a per neighbor basis. And I think that's why we still see in the local routing table of router 7, why we see that globally it shows that those routes are suppressed, because we're applying the unsuppressed map to the individual peers. Now, let's say at the same time we're trying to do some other attribute manipulation. Maybe we're doing AS path prepending, or we want to include some sort of autonomous system in the path, say AS51, and we're going to prepend that multiple times as the updates go from router 7 over to router 3. So we're going to say as we send out an update out the direction, we're going to add AS51 a couple of times. We'll add it, maybe 2 or 3 times, and it would be very simple to do, right? We would just go into router. Let me get in here. Config T, route map, prepend. All right, and I'm going to set the AS path prepend, and set AS path prepend. There we go. 51, 51, 51. Okay. Then under the BGP process, when I send updates out to router 3, I'm going to prepend out. So I'll go into router BGP 51 and do neighbor 37.3. And we're going to do route map prepend out. Okay. Also notice, by the way, on the unsuppressed map, when we applied that, there was no implicit, there was an implied direction. There was no specified direction, because obviously this is going to be a property that we're going to apply outbound to the peer. All right, so let's do a clear IP BGP star out. And what we'd expect to see for all the routes that we're learning over router 3, that we should notice that the AS path is listed on those routes. So do show IP BGP. All right, and we certainly see that for 7, and we see it for 128. But guess what we don't see? We don't see it for the 141 or the 143, right? And this is what I was talking about previously. Normally you would say, okay, if I'm doing AS path prepending, is that prepending is going to apply to any prefix, but it's only being applied to the prefixes that are part of the regular routing process, not the prefixes that are being leaked out. So we didn't get the attribute change in the individual subnets that were being unsuppressed. So if we look at this from a more general point of view, there are 5 different prefixes that router 3 or router 7 is advertising out to router 3. We have a route map that's going out. There's no conditions that we're setting inside of that route map, right? We didn't set any conditions inside the route map. And we were matching on a prefix list and taking a look at that route map, which we just did. We would assume that the prepend route map should apply to everything, right? Because if there's no match condition, in this particular case on our prepend route map, do show run pipe section route map. If you look at the prepend route map, we didn't have any set conditions. We actually didn't even really have, we had a set condition, excuse me, setting the AS path prepend, but we had no match conditions specifically. And if you have no match conditions specifically, wrong router, let's try that again on the right router. Do show run section route map. Now, if we look at this on the prepend route map, again, we're setting a condition, but we're not matching a particular condition. And when we don't match a specific condition, normally we would assume that we just simply apply this to everything because there's no match. If there's no match, I'm talking about this specific route map right here. Where's prepend? Because there's no specific match being applied, that means that it implicitly matches everything. So every prefix that we send out to the neighbor, we should be adding 51, 51, 51, 51. But only a couple of these prefixes actually had the prepending applied. And that has to do with the aggregate and how we actually do the aggregation. And the attributes are not applied. And the reason why is that when we're looking at the updates that go out to the neighbor, based on the route map conditions, the route map outbound gets processed before the unsuppressed map is processed. Now what that specifically means is that when the route map went to make the change to the AS that prevented the subnets, those subnets did not yet exist in the process, right? Because they were already suppressed. And so they were suppressed from the outbound rib. So basically it's kind of like an order of operations issue. If we did want to do the prepending for this particular case, for those particular routes, we would have to do that in a different location, right? But just something to be aware of. I doubt that you'll see anything like this, on the test, but it kind of breaks a lot of the rules that we learned previously when we were talking about order of operations and so on. All right, so there has to be some pre-planning done. Maybe we have to set up a community, or it could be setting a multi-exit discriminator. Unless the match can occur based on the correct order of operations, you might not end up with the actual result that you want. So generally in these types of cases, you want to apply the settings prior to doing the unsuppressed map. All right. There is a finite order that you can configure things. Oftentimes I run into situations where I kind of have to go through the process myself and try and figure out what's happening in the process and so on. But that's that's something to consider when you're dealing with these changes. Okay. All right. So that's pretty much it for our lesson for tonight. Pretty basic lesson. I just wanted to give you another option for manipulating routes within BGP. In our next lesson, it's going to be a little bit longer. We'll do that tomorrow, but we're going to be talking about BGP communities, and then we'll wrap up our BGP discussion by talking about BGP filtering. All right, so do you guys have any questions before we wrap it up for tonight? Nope.
No, not yet. Thanks.
All right, I'll go ahead and upload the video right now, and we'll plan on 7 o'clock. 6 o'clock tomorrow. We can do it a little bit earlier tomorrow. I have a 5, 6, 7. I'll see if I can change that. I have a chiropractor appointment tomorrow, but I can probably change that. They're open pretty late, so I'll modify that, and we'll try and get it started a little bit earlier tomorrow, okay? I'm not going anywhere. I don't have to pick up my kids, so we should be good to go. All right, so I'll see you guys in our lesson tomorrow.
All right, thanks, Scott.